Okay, so we got this awesome. So we got a list of equations now that we've generated. So we know that we got elastic energy quantified, we got kinetic energy quantified, and now we also have gravitational energy quantified. So now let's use it to make some useful predictions using the law of conservation of energy. So we're just going to start out with a generic problem, and I'm going to show you how it's worked, and then you guys are going to work on real-world problems that I'm going to actually provide to you via video and data collection. Sounds cool, right? Anyways, a cart with a mass of 15 kilograms was pressed up against a spring with a spring constant of 100 newtons per meter. If the spring was compressed by 4 meters, how fast would that car be moving on a frictionless surface? So as you can see from the picture, we have a position A and position B. So this is the culmination of everything we've been working on thus far, and it's all going to tie together right here. So at position A, let's talk about first what type of energy is present. It's compressed up against a spring, so therefore that means it has elastic energy. So I'm going to double click here. We know it has elastic energy. It's on the ground, and so it has elastic energy. It's on the ground, so it has no gravitational energy, and it's not moving at position A because it's compressed back up against a spring. So I'm going to put all of my energy bars in the elastic. Notice it's car and spring, and then at position B, it's moving. So therefore, we're going to say that all of that energy is kinetic energy. So I'm going to move it over here like so. Boom. So the step one on these problems, you need to be able to identify the energy transfer that's happening. That's like the very first thing we did in this unit. So then what we did was we now know how to also make energy conservation equations from the LOL chart. So I can say EEL at position A is equal to EK at position B. And so now I've got good information. Now I'm going to help you quantify the problems. So by writing what's known and what's not known. So I know that the mass is 15 kilograms. So for known quantities, I'm going to say the mass is equal to 15 kilograms. I also know that the spring constant is 100 newtons per meter. So I'll go K is equal to 100 newtons per meter. And then I also know that the spring was compressed. So delta X, I'm just going to put X, is equal to, what was it, 4 meters? Yeah, 4.0 meters. And so that's what I know. Now, what I don't know is how fast the car would be moving. In other words, I want to know the velocity, question mark. So now that I know a list of known and unknowns, now I'm going to determine the velocity of car B. To do that, I'm going to copy and paste this equation that I just had down here. Now, I need to find the appropriate equation that's going to help me with the elastic and kinetic energy using my equation list here. So I need to pick an elastic energy equation that has some known, because I know that I want to solve for velocity, which is related to kinetic energy. I need to pick an elastic energy equation that's related to this right here. So for the elastic energy, I know the spring constant and the displacement. So when I look at my equation list, I'm going to say, well, is there an elastic energy equation that has spring constant and displacement? There sure is. So I'm going to use that guy. So I'm going to say, well, I want to determine that the elastic energy is 1/2 of K times delta X squared. And then I need to set that equal to my kinetic energy equation, which I know is 1/2 mv squared right here. So therefore, I'm going to say that's equal to 1/2 mv squared. So now I just need to plug in my known values. So I'm going to go 1/2 of the spring constant, which is 100 newtons per meter. And then I'm going to multiply that times the displacement of 4 meters squared. I'm going to set that equal to 1/2 times the mass, which was 15 kilograms, times the velocity squared. Now, you can calculate all of this, but I'm going to help simplify this a little bit because since you have half on both sides, you can cancel those out. And so therefore, I'm going to do that. And then you're going to have, so then we'll just take this to my calculator. The whole thing should be squared. So 4 squared is 16. 16 times 100 is 1,600. So therefore, I'm going to get my calculator. I'll show you 16 times 1,000 is 16,000. And then we're going to divide that by the mass of 15. And so that's a number. Now you're thinking, whoa, that's a very large velocity. But wait a minute, pump the brakes now, because the equation, all we did was divided 15 to both sides. We have v squared here, so we still need to square root that. So I'm going to square root my answer, and then I'm going to get my velocity of 32.6, 32.7. V is equal to 32.7 meters per second. And that is how you determine velocity, and how you can use the law of conservation of energy and these quantification of energies to now make predictions about it. So what I just did was, if this spring is going to be compressed 4 meters, I now know that the velocity of that car when it leaves, assuming frictionless surface, is going to be 32.7 meters per second.